In all of our previous examples, we were looking at the atomic mass of elements by reading that average atomic mass off the periodic table to determine how much was in 1 mole of the given element. But we also have to be able to calculate the mass of our compounds in 1 mole. If we were to add or sum together all of the atomic masses of the atoms that make up a given compound, that would tell us the overall molecular mass or formula mass of our compound. Specifically, molecular mass or molecular weight is the term used for molecular compounds. That's when we have 2 or more nonmetals together in some fixed ratio by mass. Formula mass or formula weight is the term used to describe the mass of an ionic compound. That is when we have a metal with a nonmetal, or we could also have a metal with a polyatomic ion, and we would still use the term formula mass. So very specifically, if we have 1 mole of molecule X, that means the molecular mass of X in grams would be calculated by determining the atomic masses of all the atoms that make up our molecule. Same thing, if we have 1 mole of an ionic compound, that would be the formula mass of X in grams. So when we're dealing with compounds, if we want to figure out what the either formula mass or molecular mass is for 1 mole of the compound, we have to calculate it. We can't just take it right off the periodic table. So what is the formula mass of NaCl? Or what is the mass of 1 mole of NaCl? We would look at each element in the compound individually. And remember, there's a 1 that's unwritten after both of those. So we have 1 sodium atom and 1 chlorine atom in the compound sodium chloride. So if we look at the periodic table, sodium has an atomic mass of 22.9 grams per mole. And we're going to want to add that to the atomic mass of our 1 chlorine atom, which is 35.5 grams per mole. When we take the parts and we sum them together, that will give us the formula mass, which is about 58.4 grams per mole for 1 formula unit of sodium chloride. And then looking at a molecule, something like sucrose, which is table sugar, what is the molecular mass of sucrose? This time we have 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. So we have to consider how many atoms there are of each type by multiplying by them. So we've got 12 times the atomic mass of carbon, which is about 12.01 grams per mole, plus we have 22 for hydrogen times the atomic mass of hydrogen, which is about 1.01 grams per mole. And lastly, we're going to add our oxygen, which we have 11 oxygen atoms, times the atomic mass of oxygen, which is about 16 grams per mole. And if we calculate that, that'll give us the molecular mass of sucrose, which we should get about 342 grams per 1 mole of sucrose. So whenever we have a compound, we actually have to calculate the either formula mass or molecular mass. Now, using all of these different terms that really essentially mean the same thing can get a little confusing. So often for simplicity, we will refer to all of them as the molar mass. So whether we're talking about an element, which we would call the atomic mass, a molecule, which would be the molecular mass, an ionic compound, which would be the formula mass, instead, whether we're determining it for an element, molecule, or ionic compound, it doesn't matter. We'll just call it the molar mass. So 1 mole of anything, we could find the molar mass of it in grams. And then this way, we're not worrying about distinguishing between all different types of elements and compounds. We need 0.254 moles of iron 3 chloride for an experiment. How many grams do we need to weigh? So in order to answer this, we have to be able to do a couple things. First, we have to be able to take our iron 3 chloride from its systematic name and be able to write a formula. So iron 3, that's a transition metal, and we're being told the charge in Roman numerals, that's a 3+. Chloride is a group 7A nonmetal, so that means we know the charge is always going to be a -1, and we can swap our numbers in order to write our neutral formula, which will be FeCl3. Next, we need to be able to calculate the molar mass. In order to convert between moles of our compound and what we're working towards, which is grams, we're going to have to use the molar mass as our conversion factor. But now, since we have a compound, it's up to us to calculate it. So for iron 3 chloride, we're going to want to take into account that we have 1 iron atom present, and iron from the periodic table is 55.85 grams per mole. Plus, we're going to have to figure out for chlorine, which we have 3 of them, so we're going to multiply 3 times the atomic mass for chlorine, which is about 35.5 grams per mole. So for our molar mass, we should get approximately 162.2 grams per mole for our compound. Now going back to the problem, we're starting with 0.254 moles. So 0.254 moles of our compound, FeCl3. And when we use our molar mass, which we just calculated, we're going to have to put moles in the denominator and grams in the numerator so our moles can cancel. 1 mole is equal to 162.2 grams. Our moles will cancel and we'll be left in units of grams. And we should get about 41.2 grams of our iron 3 chloride compound that we would need to weigh. How many grams is 3.0 times 10 to the 24th molecules of SO3? So in this example, we're starting in particle units of molecules, and we're trying to work backwards to units of grams. So we begin in molecules, then we're going to have to work to moles, and then finally to units of grams. Our particle unit is no longer atoms because we have a compound, SO3, which is sulfur trioxide. So we have 2 or more nonmetals together in a fixed ratio, hence it's a molecular compound. We're going to need to calculate the molar mass of our compound, which will be equal to the atomic mass of 1 atom of sulfur, which is about 32.1 grams per mole, plus 3 times the atomic mass for oxygen, which is about 16 grams per mole. We can calculate and get about 80.1 grams per mole for our molar mass. In order to convert between molecules, which is our particle unit, and moles, we're going to have to use Avogadro's number. And then to convert between moles and grams, we're going to have to use our molar mass we just calculated for sulfur trioxide. So we're going to start with 3.0 times 10 to the 24th molecules. And then using Avogadro's number, we know that 1 mole of anything is 6.022 times 10 to the 23rd, in this case, molecules. And then lastly, we're going to use the molar mass to convert between moles and grams. Our mole is going to have to go in the denominator, and we determined that 1 mole was equal to 80.1 grams for our compound. So our molecules will cancel, our moles will cancel, and we'll be left in units of grams. And we should get about 399 grams of our sulfur trioxide. Now, just a note, it's easy to want to take the word molecule and abbreviate it with MOL in a period. Do not do this. A molecule is not equal to a mole. Mole is a unit that's kind of like a dozen, and the unit is MOL without the E. There is not a short unit for the word molecule, so it's best to just write the entire word out. We can also write mole-to-mole conversion factors using the subscripts within a chemical formula. The subscripts will tell us the mole ratio between the different elements within a compound. So if you remember a few slides back, we did an example using iron 3 chloride, which was FeCl3. And maybe for a given experiment, we're really only interested in the amount of iron in the compound and not the chlorine. We could determine then exactly how much iron we would need for an experiment by comparing the amount of iron to the amount of chlorine within the compound itself. So we have an unwritten subscript of 1 after the iron, and we have a subscript of 3 after the chlorine. We can write mole-to-mole relationships between these subscripts as well as to the overall compound. So let's imagine that we have just one water molecule, like we see on the left. The white spheres represent the hydrogen atoms, and the red spheres represent the oxygen atoms. So if we're just looking at the picture, we can see that for every one molecule of water, there is 2 atoms of hydrogen. We can count them. If we have one molecule of water, we can see that we have 1 atom of oxygen. We can also look at how the oxygen compares to the hydrogen in the one water molecule. For every 1 atom of oxygen, there's always 2 atoms of hydrogen. That's what our formula actually tells us, H2O. Now, whether we just have one molecule of water this holds true, this same relationship would hold true if we have 2 molecules, or if we had a dozen molecules. That's still going to always have the same oxygen to hydrogen relationship if it's water. So since a mole is just simply a counting term, just like a dozen, we can use mole relationships as well. 1 mole of water would always be 2 moles of hydrogen. 1 mole of water would always be 1 mole of oxygen, and we would always have 1 mole of oxygen for every 2 moles of hydrogen in our compound of water. So this is specifically looking at the given subscripts for a compound and comparing them to each other and to the overall compound. Let's think about what mole-to-mole conversion factors we can write for the formula P4O10. If we were to name this, this would be tetraphosphorus, and then the prefix for 10 is deca, but we say decoxide. So looking at our P4O10, we can compare our subscripts to the overall compound. So for phosphorus, we have 4 phosphorus atoms, and for oxygen, we have 10 oxygen atoms. We can say there's 4 phosphorus, 4 moles of phosphorus for every 1 mole of tetraphosphorus decoxide. Or we can say there's 10 moles of oxygen for every 1 mole of P4O10. Lastly, we can write a relationship between the 2 things that make this up, which is phosphorus and oxygen. 4 moles of phosphorus is always going to be equal to 10 moles of oxygen in this compound. Those are 3 conversion factors that we can write, and we could convert them into fractions and use them how we need to in a problem. Let's try an example using our new mole-to-mole relationships. Calcium phosphate is found in bones and some kidney stones. In one case, a sample is found to contain 0.864 moles of phosphorus. How many moles of calcium phosphate are there in that sample? So we know moles of our element phosphorus, and we want to work from our phosphorus back to moles of the overall compound calcium phosphate. So we're going to need to first be able to write a proper formula for calcium phosphate. Calcium is a group 2A metal. It always forms a +2 charge in ionic compounds, And phosphate is one of our polyatomic ions, and that is PO4 3-. So we're going to put a 2 after our phosphate units and a 3 after our calcium. So our formula here would be Ca3, parenthesis, PO4, and then 2 after our parenthesis, because we have 2 phosphate units. So now when we look at this and we want to determine the relationship between our subscripts and our overall formula, or our overall compound, our 2 is on the outside here. So really what that means is the 2 could be distributed to the oxygen and the 2 could be distributed to the phosphorus, which is what we're looking for in this example, is the phosphorus specifically. So we can write our relationship here as 2 moles of phosphorus are equal to 1 mole of our calcium phosphate, Ca3, parenthesis, PO4, 2. Now, we know that we have 0.864 moles of phosphorus. That's what we were told in the problem. And we want to convert moles of phosphorus to moles of calcium phosphate. So we can use our conversion factor we just wrote. Moles of phosphorus will go in the denominator. And we know that there are 2 moles of phosphorus for every 1 mole of our compound, Ca3PO4 2. Our moles of phosphorus would cancel, and that'll give us moles of calcium phosphate. So we're going to divide by 2. We should have 0.432 moles of our calcium phosphate. Let's try another one. How many grams of iron are needed to combine with 25.6 grams of oxygen to make the compound iron 3 oxide? So first let's write our correct formula for iron 3 oxide. Iron is Fe and it's iron 3, so it has a 3+ charge. Oxygen is a representative element, group 6A, always forms a -2 charge. So we're going to cross our charges as subscripts to get our neutral formula. Remember, we never want to leave charges in our formula, otherwise it would be wrong. So we're going to end up with Fe2O3. And in this example, we're trying to figure out grams of iron, and we know specifically grams of oxygen. So in this case, we're starting with oxygen and working towards iron. And if we write a relationship for our subscripts here, 3 moles of oxygen are always equal to 2 moles of iron, according to our chemical formula. So we're going to start with our grams of oxygen. And in order to use our relationship that we wrote, we have to be in moles. So we're going to convert our grams of oxygen to moles of oxygen. And then we're going to use our conversion factor to go from moles of oxygen to moles of iron. And then lastly, the question asks for the grams of iron. So we're going to have to convert back to grams of iron. So first we're going to need to use our molar mass to convert to moles of oxygen. And then we're going to have to use our subscripts to convert between moles of oxygen and moles of iron. And then lastly, we'll go back to grams of iron using the molar mass for iron. So starting off, we have 25.6 grams of atomic oxygen. Notice this is not O2 or diatomic oxygen. There's no subscript 2 after that. And looking at the periodic table, what is our molar mass of oxygen? 1 mole of oxygen is equal to about 16 grams. We put grams in the denominator so they cancel. So we have moles of oxygen in the numerator. Now we want to use our mole-to-mole ratio that we wrote at the top. 3 moles of oxygen for every 2 moles of iron. We had to put moles of oxygen in the denominator, so they would cancel. Right now we could see our grams of oxygen cancel, our moles of oxygen cancel, and we're in moles of iron. So we have one more step. We have to convert moles of iron into grams. If we look at the periodic table, the molar mass of iron, 1 mole of iron is going to be 55 0.85 grams of iron. Our moles of iron will cancel, and we'll be left in units of grams, which is what we were after. When we calculate this, we should get approximately 59.5 grams of the iron that would be needed to combine with that mass of oxygen to form iron 3 oxide. We just learned that the chemical formula provides us with information about the mole ratio between the elements within a compound. Percentage composition is another way of providing us with the information of how much a specific element makes up a compound in a percent. So percent composition is usually a list of all the elements that are in a given compound and their percentage by mass. So percentage by mass is calculated by determining the mass of one element within a compound, and we would multiply by how many atoms of that element there are, and we divide by the mass of the entire sample, and then calculate it as a percentage, so multiply by 100. This percentage by mass data is often useful in a variety of calculations that we'll see in a little bit. Elemental analysis is one way to use mass percentage data. Elemental analysis is where there is an unknown compound that is often decomposed to find the masses of the elements that are within a given compound. We can determine empirical formulas, which are those simplified formulas. And an empirical formula will only tell us the smallest whole number ratios of a compound. We can work backwards from some other information to figure out the true molecular formula from an empirical formula. There are three major ways that we'll learn to calculate empirical formulas. First, from percent composition data. Second, from mass data, which percent composition and mass data really tell us essentially the same thing. So the method here is really the same thing. And the third way that we'll learn in Chapter 4 is called combustion analysis. We can determine empirical formulas indirectly by taking an unknown sample and combusting it and determining the products that are formed from that combustion and working backwards to figure out what the unknown sample was made of. In Chapter 3, we're only going to focus on percent composition and mass data. Let's do an example of calculating an empirical formula from percent composition data. A white powder is used in paints, enamels, and ceramics, and it has the following percent composition: 69.6% barium, 6.09% carbon, and 24.3% oxygen. What is the empirical formula, or the simplest formula, and what is the name of this compound? So whenever we're given percent composition data, we can essentially cross off the percentages and pretend that those are grams. We can use this as masses to convert to moles. If we can take our grams, so first we take our percentages and we list them as grams, and then from our grams, we can determine the number of moles. And the moles we figured out tell us something about the subscripts. If we can determine the subscripts, then we can figure out what the formula is, which is our goal. We're trying to figure out an empirical formula. So individually, let's take all of our masses, so 69.6 grams of barium, and we're going to convert them into moles. The atomic mass of barium from the periodic table is about 137.3 grams per mole, and that'll give us about 0.069 moles of barium. Next, we know that the compound has some carbon in it, so 6.09 grams of carbon, and the molar mass of carbon is 12.01 grams. So we can calculate our moles of carbon, 0.5071. moles of carbon. And we know it has some oxygen in it. 24.3 grams of oxygen. We'll convert that to moles. 1 mole of oxygen is about 16 grams. And that gives us about 1.519 moles of oxygen. Now, once we have all of our mole ratios between our subscripts, we have to figure out what is the smallest whole number ratio between them all. We can't write barium 0.569, carbon 0.5071, and oxygen 1.5. They always have to be small whole numbers. So the easiest way to do this is to take the smallest one, which in this case is barium, and divide all 3 moles by the smallest number. So we're going to take the number for barium, the moles, which is 0.5069, and we're going to divide it by itself. Then we're going to divide the moles of carbon by this number. And then lastly, the moles of oxygen by this number, because this was our smallest one. So we divided all of the moles by that smallest one. And when we divide the moles of barium by itself, we should get 1. When we divide, notice the moles of carbon and the moles of barium were about the same. That should give us about 1 as well. And when we divide the moles of barium into the moles of oxygen, that should give us about 2.99, which is close enough to 3 to round it up. We'll see later that sometimes we have to actually multiply by another number to find the smallest set of whole numbers. But if they're pretty close to a whole number, we can round. So now that tells us the smallest set of whole numbers. So we have Ba1, C1, and then O3 in our chemical formula. And how would we name this? This would be barium, and then CO3 is carbonate. So this is our empirical formula, or our simplest chemical formula. And since barium carbonate is an ionic compound, it makes sense that the empirical formula is actually the true formula, since BaCO3 is a formula unit for this compound, since it is ionic. Calculating an empirical formula from mass data. When we're given mass data, essentially we're given the same information as percent composition. You saw in the previous example that we crossed off the percentages and simply listed them as grams. Mass data is where we're provided with our masses in grams already in the problem. So I can see that I already have some masses in here. Determine the empirical formula for a compound of iron and oxygen called black iron oxide. When a 2.44 gram sample is analyzed, it is found to have 1.771 grams of iron and 0.677 grams of oxygen. So just like before, we're going to take our grams of each element and convert it to moles. We know that our moles will tell us about the subscripts. And we know that we're going to have to figure out the small whole number ratios between those subscripts if we're going to write a formula. We can't have any decimals or fractions in our formula. So let's start with iron. We have 1.771 grams of iron, and we're going to convert that to moles. So looking at the periodic table for the molar mass of iron, it's about 55.85 grams per mole. And when we calculate our moles of iron, that's going to be 0.0317 moles of iron. And then we'll take our mass data for oxygen. We know that the sample has 0.677 grams of oxygen. And from the periodic table, the 1 mole of oxygen is about 16 grams. So that gives us 0.0423 moles of oxygen. Now, what we did last time, we're also going to do, we're going to take our smallest mole ratio, which is for iron, and divide everything by that. So 0.0317 moles divided by our moles for iron and our moles for oxygen. Our moles for iron is simply going to give us 1 when we divide them because we're dividing a number by itself. And when we divide for oxygen, we're going to get 1.33. Now this isn't close enough to 1 for us to round down to 1. It's not close enough to 2 for us to round up to 2. So if we were to stop and write our chemical formula right now, we would have Fe1O 1.33. But we can't leave it like that because we can't have fractions or decimals. So sometimes we actually have to multiply through by something in order to figure out the smallest set of whole numbers. This table shows us some examples of numbers we might multiply by depending upon the decimal we get. So for example, if we had 0.2, that means a fraction of 1/5. So we would end up multiplying by 5. 0.25 is 1/4. We would multiply by 4. And what we just got was 0.33, which means 1/3. So we're going to have to multiply by 3 to get small whole numbers. You'll see with some practice problems that you usually end up having to multiply through by 2, 3, 4, or 5 commonly in order to come up with a whole number if you run into this situation. So since we're going to multiply through by 3, that means the 3 will get multiplied through to the 1.33 and to the 1. We have to distribute it to everything in our formula. So this will give us a formula of Fe3O, and when we multiply 1.33 by 3, we should get 4. This is going to be our empirical formula or our simplest formula for our compound. We previously learned 2 ways to determine empirical formulas, which are simplified formulas. If we want to determine the molecular formula for a compound, in other words, the true or real formula, we have to know a little bit more information. Specifically, we have to be told the molecular mass for that true formula. If we know the molecular mass and our determined empirical formula, we can figure out how many empirical formula units, or EFUs, are within a given molecular formula. So the molecular mass will be for our true compound, which we're trying to determine the formula for, and we'll divide by the empirical formula mass. This empirical formula mass will be something we have to calculate from our formula, from our empirical formula that we previously determined. So let's try an example. The empirical formula was determined to be C2H6O. If the molecular mass was found to be 138 grams per mole, what is the molecular formula? So this molecular mass we're being given, 138 grams per mole, this is what we'll refer to as the true or real mass for that molecular formula. We'll calculate first the number of empirical formula units contained within our chemical formula. So first we got to take our true molecular mass and divide by our empirical formula mass. We know our true molecular mass. We were given that in the problem, 138 grams per mole. But what about our empirical formula mass? We were told, or we could calculate by any of the methods we learned previously, that the empirical formula is C2H6O. So we have to calculate that empirical formula mass. That'll be equal to 2 times the molar mass of carbon, which is 12.01 grams per mole, plus 6 times about 1.01 grams per mole for each hydrogen, plus about 16 grams per mole for our oxygen. Our empirical formula mass should come out to around 46 grams per mole for this compound. So we're going to plug that into our denominator. 46 grams per mole is our calculated empirical formula mass. So when we divide, notice our units of grams per mole are going to cancel, and we're just going to be left with a whole number. So 138 divided by 46 should be 3. And we would expect a whole number here because we want a whole number of our units to be in one of our molecular formulas. That means that if C2H6O is our empirical formula, we're going to multiply through by 3 to each of our subscripts to get our true molecular formula. So 3 times 2 for carbon, 3 times 6 for hydrogen, and 3 times 1 for oxygen. So that means that our molecular formula is going to be C6H18O3. And that's going to be our true formula for the compound. So the only way we can actually figure out what the molecular formula is from the empirical formula is if we know the molar mass of our true compound.